Picture this: a world plunged into endless winter, where the sun struggles to pierce a sky choked with ash, and the very air turns thick with the scent of sulfur. This isn't some distant nightmare or the plot of a sci-fi film. 74,000 years ago, it was our reality, beneath the tranquil surface of what is now Lake Toba in Indonesia. A force of unimaginable power stirred. The Toba supervolcano erupted with a fury so vast it spewed enough debris to blanket continents, triggered a volcanic winter that lasted decades, and pushed humanity to the edge of extinction. Today, we're going to uncover the story of this cataclysmic event, how it reshaped our planet, altered the course of human evolution, and left scars that scientists are still deciphering. What makes Toba so fascinating isn't just the scale of its destruction, but the mystery of how our ancestors survived it. Genetic studies suggest that at one point, the human population may have dwindled to just a few thousand individuals, a genetic bottleneck that echoes through our DNA even now. Imagine the courage, the resilience it took to endure years of freezing temperatures, dwindling food sources, and a world transformed into a wasteland. This isn't just a tale of disaster, it's a testament to human tenacity, a story of how we clung to survival against impossible odds. As we peel back the layers of time, you'll discover how modern science has pieced together clues from ice cores, ancient tools, and even the genetic blueprint of our species to reconstruct this pivotal moment in history. From the ash-covered landscapes of the past to the cutting-edge research of today, this journey will challenge everything you thought you knew about humanity's most fragile and triumphant chapter. So settle in, because we're about to travel back to a time when the fate of our species hung by a thread, and uncover the supervolcano that almost erased us from existence. To understand why supervolcanoes like Toba stand in a league of their own, we need to look beneath the surface, literally. Unlike the dramatic cone-shaped volcanoes we're familiar with, supervolcanoes form over massive magma chambers, some stretching dozens of kilometers wide. These chambers aren't just big, they're pressurized time bombs, simmering for hundreds of thousands of years until the Earth can no longer contain them. When they finally erupt, they don't just blow their tops, they collapse inward, creating vast depressions called calderas. Lake Toba itself is one such caldera, a serene blue mask over the chaos that once erupted beneath it. The difference between a regular volcanic eruption and a supereruption isn't just about scale, it's about world-altering power. Take Mount St. Helens in 1980, which released around 1 cubic kilometer of ash and rock. Now compare that to Toba, which unleashed an estimated 2,800 cubic kilometers of material. That's enough to bury the entire state of California under 7 meters of ash. But the real danger lies in what happens next. All that debris doesn't just settle, it's hurled into the stratosphere, where winds carry it across the globe, blocking sunlight for years. Temperatures plummet, crops fail, and ecosystems collapse. This isn't just a bad winter, it's a planetary reset button. Scientists piece together these cataclysms by reading nature's archives. Ice cores from Greenland and Antarctica hold layers of sulfuric acid, fingerprints of ancient eruptions. Geological records show ash deposits as far away as India and East Africa, proof of Toba's far-reaching fury. And then there's the genetic evidence. Studies of modern human DNA suggest our ancestors faced a population crash around the same time, a chilling clue about how close we came to vanishing. What's truly humbling is realizing that supervolcanoes aren't relics of the distant past. Beneath Yellowstone National Park, another magma chamber stirs, one that's erupted before and will erupt again. The question isn't if, but when. And while we can't stop these forces, understanding them might just be the key to our survival next time the Earth decides to rewrite history. 74,000 years ago, the ground beneath Sumatra trembled with a force beyond comprehension. Deep within the Earth, pressure had been building for millennia until finally, the Toba supervolcano could no longer contain its fury. The eruption that followed didn't just shake the island, it shook the entire planet. Think of the loudest sound you've ever heard, a thunderclap, an explosion, then multiply it by 1,000,000. That's Toba. The blast was so immense, it's believed to have reached a volcanic explosivity index of 8, the highest possible rating. To put that in perspective, it released energy equivalent to 1,000,000 Hiroshima bombs detonating simultaneously. The immediate aftermath was apocalyptic. Towering columns of ash and gas punched through the atmosphere, reaching heights of over 40 kilometers. Rivers of molten rock incinerated everything in their path, while pyroclastic flows, superheated avalanches of gas and debris raced across the land at hundreds of kilometers per hour. But the real devastation came from what happened next. As the ash spread, it formed a thick, global shroud blocking sunlight for years. Temperatures plummeted by as much as 10 degrees Celsius worldwide. Trees withered, animals starved, and acid rain poisoned freshwater sources. For the small bands of humans struggling to survive, it must have felt like the end of the world. What's truly staggering is the sheer volume of material Toba ejected, enough to bury entire mountain ranges. The ashfall was so thick, traces of it have been found over 4,000 kilometers away in India, layered like a ghostly fingerprint in the soil. In some places, the deposits reach heights of 6 meters, a stark reminder of nature's raw power. And at the heart of it all, the Earth itself collapsed, leaving behind a gaping wound, a caldera so vast it eventually filled with water, becoming the serene Lake Toba we see today. Yet amid this devastation, something remarkable happened. Against all odds, humanity endured. Genetic studies suggest our ancestors weathered this catastrophe in isolated pockets, perhaps clinging to coastal refuges where marine resources offered a lifeline. Their survival wasn't just luck, it was adaptability, resilience, and an unyielding will to persist. The scars of Toba are etched not just in the landscape, but in our very DNA, a silent testament to the day the Earth shook and humanity held on. The genetic bottleneck theory is one of the most haunting chapters in our species' story, a moment when humanity's flame flickered dangerously close to extinction. When scientists first analyzed the genetic diversity of modern humans, they made a startling discovery. Our DNA tells a story of drastic reduction, a time when the human population may have shrunk to just a few thousand breeding pairs. This bottleneck left its mark in our genes, with all of today's 7 billion people descending from that tiny, resilient group. The timing aligns eerily with the Toba eruption, suggesting these survivors may have weathered the volcanic winter that followed. But how could a single event nearly erase an entire species? Imagine a world where ash blotted out the sun for years, triggering a chain reaction of ecological collapse. Plants withered without sunlight, herbivores starved, and predators followed. For early humans relying on hunting and gathering, this would have been catastrophic. Some researchers estimate global temperatures dropped by as much as 10 degrees Celsius for nearly a decade, turning fertile landscapes into frozen wastelands. In such conditions, only those in isolated refuges, perhaps coastal regions where marine life persisted, would have had a fighting chance. Not all scientists agree on the severity of Toba's impact. Some argue the genetic bottleneck could have resulted from other pressures, like disease outbreaks or competition with other hominid species. Others point to archaeological evidence showing human tools both before and after the eruption, suggesting continuity rather than collapse. Yet even skeptics acknowledge Toba's eruption coincided with a pivotal moment in human evolution, a time when our ancestors' ingenuity was put to the ultimate test. What's undeniable is that those who survived carried forward traits that define us today. Their resilience shaped our genetic legacy, favoring adaptability, cooperation, and problem-solving skills. The survivors of Toba didn't just endure, they laid the foundation for humanity's eventual spread across the globe. Their story is written in every cell of our bodies, a silent reminder of how close we came to vanishing and how extraordinary it is that we're here at all. Survival wasn't just about luck, it was a desperate game of adaptation played out across a planet turned hostile. As the skies darkened and temperatures plunged, early humans faced a brutal calculus: find shelter, secure food, or perish. Some groups likely migrated toward the equator, where tropical forests offered relative stability. The dense canopy may have provided protection from acid rain, while year-round plant growth and animal life became lifelines in a world where other ecosystems crumbled. Caves, too, became sanctuaries, natural shelters that preserved warmth and stored resources. Archaeologists have uncovered evidence of prolonged cave habitation during this period, with layers of ash separating deposits of tools and bones, marking the boundary between life before and after catastrophe. But survival required more than just finding refuge. It demanded innovation. The tools left behind tell a story of ingenuity under pressure. Smaller, more precise stone blades appear in the archaeological record, suggesting a shift toward efficiency. With large game scarce, humans may have turned to hunting smaller animals or processing tough plant foods, requiring tools that could extract every possible calorie from our unforgiving landscape. Even more telling are the signs of long-distance trade networks emerging in the aftermath. Shells and obsidian fragments found hundreds of kilometers from their sources hint at something revolutionary: cooperation. In a world where no single group had all the answers, sharing knowledge and resources became the ultimate survival strategy. The social bonds forged in this crucible may have been our ancestors' greatest advantage. Unlike other hominid species that vanished, humans developed ways to transmit complex information across generations, not just through instinct, but through language and culture. A child born after the eruption could learn which plants were edible, where to find clean water, or how to craft a warm shelter, not by trial and error, but from the hard-won wisdom of those who came before. This ability to pool knowledge and adapt collectively turned a handful of scattered survivors into the architects of humanity's future. What's astonishing isn't just that they endured, but how their struggles shaped who we are. Genetic studies reveal that modern humans have remarkably low genetic diversity compared to other primates, a lingering echo of that near-extinction event. Yet within that narrow band of survivors lay a reservoir of resilience, the same traits that carried them through creativity, cooperation, the ability to innovate under pressure became the foundations of civilization. From the ashes of Toba rose not just a species clinging to existence, but one poised to colonize every continent, build cities, and ultimately unravel the very mysteries of the volcano that nearly ended us. Their story is written in every innovation, every community, every time humanity faces the impossible and finds a way through. The parallels between Toba's volcanic winter and the theoretical nuclear winter are almost too chilling to ignore. Both scenarios paint a picture of our planet plunged into sudden, artificial darkness, not from the setting sun, but from billions of tons of fine particles suspended in the upper atmosphere. After Toba's eruption, sulfate aerosols formed a global veil that scattered sunlight back into space for nearly a decade. Crop yields would have collapsed as growing seasons shortened, food chains unraveled, and ecosystems buckled under the strain. This wasn't just bad weather. It was a fundamental rewiring of Earth's climate system on a scale that makes modern concerns about climate change seem almost gradual by comparison. What makes these ancient events so valuable to modern science is how they serve as natural laboratories. Climate modelers feeding Toba's eruption data into supercomputers have watched virtual skies darken and temperatures plummet in eerie simulations. The same models used to reconstruct Toba's aftermath are now applied to nuclear winter scenarios, where smoke from burning cities could mimic volcanic ashes' sunlight-blocking effects. The numbers are sobering. Even a limited nuclear exchange might lower global temperatures by several degrees, with devastating agricultural consequences. One study suggested rice production in Asia could drop by 20% for over a decade, while wheat fields from the American Midwest to the Ukrainian steppe might fail entirely. Yet there's a crucial difference between these catastrophes. Toba was a single, violent event followed by gradual recovery. A nuclear winter could involve multiple strikes, radioactive fallout, and the collapse of global supply chains, layers of chaos our ancestors never faced. This is where the archaeological record becomes unexpectedly relevant. The scattered bands of humans who survived Toba did so through localized adaptations, coastal foraging, cave networks, and small-scale cooperation. Modern civilization, by contrast, relies on fragile, interconnected systems. A single season of failed harvests could empty supermarket shelves worldwide, while power grid failures might freeze populations accustomed to central heating. Perhaps the most valuable lesson from Toba isn't just about survival, but about preparation. Early warning systems for supervolcanoes are now being tested, with satellites monitoring ground deformation around Yellowstone and other hotspots. Seed vaults in Norway and elsewhere preserve genetic diversity against agricultural collapse, while NASA even researches volcanic ash-resistant crops. These aren't just scientific curiosities, they're direct responses to the vulnerabilities Toba exposed in our species' relationship with the planet. The same ingenuity that carried a few thousand humans through the last global catastrophe may yet help billions weather the next one. What remains haunting is the realization that our technological civilization, for all its advances, still dances on the same geological razor's edge as our ancestors. The ash layers at Toba remind us that disaster isn't a matter of if, but when. The difference this time is that we can see it coming, and perhaps, just perhaps, write a different ending to the story. The idea that Toba nearly wiped out humanity makes for a gripping story, but is it entirely accurate? Digging deeper reveals a scientific debate as layered as the volcanic ash itself. While the genetic bottleneck evidence is compelling, some researchers point out that population crashes can stem from multiple factors, not just volcanoes. Prolonged droughts, disease outbreaks, or even competition with other hominin species like Neanderthals could have squeezed human numbers long before Toba's eruption. One provocative theory suggests our ancestors were already in decline, making the volcanic winter less a knockout punch than the final straw in a series of ecological blows. Then there's the archaeological counterargument. At sites like Jewalapuram in India, stone tools appear both above and below the Toba ash layer, showing no drastic shift in technology or culture. If humans were truly pushed to the brink, wouldn't we see signs of societal collapse, abandoned settlements, regressed toolmaking? Instead, some communities seem to have adapted almost seamlessly. Similarly, in South Africa's Pinnacle Point caves, evidence of shellfish harvesting and advanced tool use continues uninterrupted through the eruption period. These pockets of resilience suggest that while Toba's impact was global, its effects were far from uniform. Climate models add another wrinkle. While simulations confirmed temperatures dropped sharply after the eruption, some regions, particularly coastal areas, may have been buffered by ocean currents. Stable marine resources could explain how certain groups not only survived but flourished. This challenges the stereotype of a monolithic volcanic winter, painting instead a mosaic of microclimates where resourceful humans found niches to endure. The heart of the debate isn't just about volcanoes, it's about how we reconstruct history from fragments. A single genetic study or ash layer can't tell the whole story. What looks like a bottleneck in our DNA might actually reflect a subtler process, populations fragmenting into isolated groups rather than vanishing entirely. New techniques, from high-resolution sediment analysis to AI-driven climate reconstructions, are constantly refining our view. What emerges isn't a dismissal of Toba's power, but a nuanced portrait of human adaptability. Perhaps the real lesson isn't that we almost went extinct, but that our ancestors were masters of contingency, scattering, innovating, and cooperating their way through crises. The next time you hear a dramatic headline about humanity's near demise, remember, the truth is rarely written in ash alone. It's etched in the countless small acts of survival that no volcano could ever erase. Buried deep within the ice sheets of Greenland and Antarctica lie frozen diaries of Earth's most dramatic moments, and Toba's eruption left one of the most vivid entries. When scientists drill down through these ancient glaciers, they're not just extracting ice, they're peeling back layers of time itself. Each band of compacted snowfall, some as thin as a sheet of paper, holds chemical whispers of the atmosphere from 74,000 years ago. The real smoking gun, microscopic spikes of sulfuric acid trapped in the ice, telltale signatures of massive volcanic eruptions. At the depth corresponding to Toba's timeline, these acid concentrations are off the charts, some of the highest ever recorded in ice core history. What makes these frozen records so extraordinary is their precision. Like tree rings but with far greater resolution, ice layers allow researchers to count individual years before and after the eruption. By studying the chemical composition of trapped air bubbles, they've reconstructed how Earth's climate responded to Toba's assault. Oxygen isotope ratios reveal temperature swings. Some layers show sudden drops of 5 to 10 degrees Celsius persisting for nearly a decade. Dust particles mixed with the acid tell another story. As global temperatures crashed, arid winds scoured continents, carrying mineral grains from drying riverbeds all the way to the poles. These weren't isolated weather events, they were symptoms of a planet thrown into shock. The ice cores also solve a long-standing mystery about Toba's aftermath. Earlier theories suggested the volcanic winter might have lasted centuries, but the chemical evidence paints a more nuanced picture. While the initial decade saw the most dramatic cooling, subtle atmospheric changes persisted for generations. Thin layers of ammonium suggest increased wildfires as ecosystems struggled to recover, while shifts in methane levels hint at wetlands drying up across the tropics. Even more fascinating are the differences between Greenland and Antarctic cores. The northern hemisphere appears to have borne the brunt of the cooling, supporting the idea that human populations near the equator may have found slightly more hospitable refuges. Perhaps the most humbling realization comes from comparing Toba's ice core signature to other historic eruptions. The infamous 1815 eruption of Tambora, which caused Europe's year without a summer, barely registers compared to Toba's atmospheric disruption. Even the massive blast that obliterated the Mediterranean island of Thera 3,600 years ago left sulfuric acid levels 20 times lower. This perspective makes it clear Toba wasn't just another eruption. It was a geological event that reset the planet's climate like a cosmic thermostat, testing life's resilience in ways we're only beginning to understand. These frozen archives do more than satisfy scientific curiosity. They offer warnings. Modern climate models fed with ice core data can simulate how Earth might respond to future supervolcanic events. The same techniques used to study Toba now monitor industrial pollution's impact on our atmosphere, proving that sometimes the deepest insights into our future come from the oldest ice on Earth. As drills bring up fresh cores from increasingly remote glaciers, who knows what other climate mysteries or survival lessons remain locked in the ice, waiting to be decoded. Long before scientists drilled ice cores or analyzed genetic bottlenecks, our ancestors grappled with Toba's aftermath through stories, myths that may hold hidden truths beneath their symbolic layers. Consider the Aboriginal Australian tale of the fire being who darkened the sky with smoke, plunging the world into cold until the people learned to share fire. Or the Norse legend of Fimbulwinter, a 3-year winter that heralded the apocalypse. Even the Hindu epic Mahabharata describes a sky without light and rivers boiling with heat. These aren't isolated fables, they're recurring motifs found across continents, often tied to foundational cultural memories of catastrophe. What makes these stories so compelling isn't just their shared imagery, but their longevity. Oral traditions can persist for hundreds of generations when embedded in ritual and song. The Klamath people of North America, for example, recount a battle between the sky god Skell and the underworld spirit Lau that mirrors the actual eruption of Mount Mazama 7,000 years ago, proof that preliterate societies could preserve geological events with startling accuracy. Could Toba's eruption, far older and more devastating, have left similar imprints? Some linguists point to common root words for disaster or darkness in ancient languages as possible linguistic fossils of shared trauma. Yet separating historical kernels from metaphorical embellishment is no simple task. Myth-making follows its own logic, blending observation with symbolism. The biblical flood narrative, for instance, shares elements with older Mesopotamian tales, but was it inspired by rising sea levels after the Ice Age, local river floods, or something far older? Similarly, the global prevalence of dragon myths might reflect humanity's primal fear of wildfires sparked by volcanic lightning. Without written records, we're left reading between the lines of folklore, searching for patterns in the collective unconscious of our species. Perhaps the most tantalizing clue lies in the universality of these stories. From the Inuit to the Maori, cultures separated by oceans and millennia describe skies raining ash, winters that never end, and ancestors who survived by hiding in caves or fleeing to high ground. These parallels suggest something deeper than coincidence, a shared human experience filtered through cultural lenses. Whether these legends trace back to Toba specifically or to later eruptions, they reveal a profound truth. For thousands of years, humanity has carried within its stories the memory of a time when the world itself seemed to turn against us. The next time you hear an ancient tale of catastrophe, listen closely. Beneath the gods and monsters, there might just be the distant echo of a supervolcano's roar, and the unbroken thread of resilience that connects us to those who outlasted the darkness. The ground beneath Yellowstone National Park isn't just picturesque, it's alive. Beneath the geysers and hot springs lies one of the planet's most massive magma chambers, a sleeping giant that last erupted 640,000 years ago. Unlike traditional volcanoes with their iconic cones, Yellowstone's power comes from something far more ominous, a caldera spanning 70 by 45 kilometers, large enough to swallow entire cities whole. And it's not alone. New Zealand's Lake Taupo, formed by a super-eruption 26,500 years ago, still experiences regular seismic activity, reminding us that these geological titans are merely dormant, not extinct. What makes modern supervolcanoes so unnerving isn't just their destructive potential, it's our inability to predict when they might awaken. Current monitoring systems read the Earth's vital signs like a doctor checking a patient. Satellites measure ground inflation to the millimeter, while networks of seismometers detect even the faintest tremors. At Yellowstone, the ground has risen and fallen by meters over decades as magma shifts below. But here's the catch: these signals don't always mean an eruption is imminent. The Earth gives warnings, but they're written in a language we're still learning to decode. In 2008, rising magma beneath Chile's Chaytane volcano triggered evacuations just 30 hours before it blew, a rare success story. For supervolcanoes, we might only get months or years of notice, if that. The aftermath of a modern supereruption would rewrite civilization. Picture ashfall measured not in centimeters, but meters, collapsing roofs from Minneapolis to Memphis. Air travel would halt as abrasive particles ground jet engines to a standstill. The real crisis would unfold in global agriculture. Sulfur aerosols blocking sunlight could slash crop yields by 70% for years, not just in the eruption's shadow, but worldwide. Supermarket shelves would empty within days, and food riots could eclipse any in recorded history. Unlike the scattered hunter-gatherers who survived Toba, today's 8 billion people rely on just-in-time supply chains with razor-thin margins for disruption. Yet there are glimmers of preparation. NASA has explored radical concepts like drilling into Yellowstone's magma chamber to siphon off heat gradually. Global seed vaults in Svalbard and elsewhere preserve genetic diversity against agricultural collapse. Some countries stockpile grain reserves, while advances in vertical farming and lab-grown foods offer potential workarounds for sun-starved crops. The most critical defense, though, may be knowledge itself. By studying Toba's aftermath, we've learned resilience isn't about preventing disaster. It's about adapting faster than the crisis unfolds. The question isn't whether another supereruption will happen, it's whether we'll heed the warnings written in ancient ice and stone. Unlike our ancestors, we can see the threat coming. The challenge now is to build a world flexible enough to bend without breaking when the Earth finally speaks again. Yellowstone's grandeur hides a geological secret. 3 cataclysmic eruptions mark its violent past, each rewriting North America's landscape. The oldest, 2.1 million years ago, ejected enough material to bury Texas under 5 meters of ash. Then came the Henry's Fork eruption 1.3 million years later, carving out a caldera visible from space. But it's the youngest, the Lava Creek eruption 640,000 years ago, that haunts scientists today. That single event spewed 1,000 cubic kilometers of rock and ash, leaving a crater 50 kilometers wide. To grasp that scale, imagine an explosion so vast it could fill the Grand Canyon twice over with volcanic debris. Monitoring this sleeping giant is a 24/7 operation. Hundreds of seismometers dot the park, tracking even the slightest tremors. GPS stations measure ground deformation down to the millimeter, while gas sensors sniff for increases in sulfur dioxide, a potential magma warning sign. In 2008, these instruments detected something unusual. Over 3 days, more than 500 small quakes rattled the park, followed by the ground swelling by nearly 20 centimeters. Panic spread online, but scientists quickly clarified. This was likely hydrothermal fluids shifting, not magma rising. Such false alarms reveal the delicate dance of prediction, separating normal geological size from true danger signals. Evacuation plans exist, but they strain credibility. Yellowstone receives over 4 million visitors annually, with peak summer months seeing nearly 30,000 people in the park daily. Roads designed for scenic drives would become death traps in a mass exodus. The nearest major cities, Salt Lake City, Denver lie hundreds of kilometers away, their highways ill-equipped for sudden refugee waves. Even with perfect warning, logistics collapse under the numbers. Where would millions go? How would supply chains feed them? The cold truth is that in a sudden eruption, many wouldn't make it out. Yet preparedness isn't hopeless. Iceland's 2010 Eyjafjallajökull eruption taught valuable lessons in ash cloud management, while New Zealand's Toba volcanic zone has drilled evacuation scenarios for decades. Some experts propose volcano taxis, pre-positioned buses and aircraft for rapid tourist extraction. Others advocate for real-time monitoring apps that could ping visitors' phones with evacuation routes the moment sensors detect danger. The deeper solution lies in public education, helping people understand that Yellowstone isn't just a tourist attraction, but a living, breathing geological force. What keeps scientists awake at night isn't just the eruption itself, but the cascade of failures that would follow. Modern society depends on systems with no redundancy. A single ash-clogged power transformer could black out half the Midwest. Airborne silica particles would shred jet engines, grounding global air travel. Crops would fail under ash-choked skies, triggering food shortages in nations never touched by the blast. Unlike our ancestors who weathered Toba in small, mobile groups, we've built a civilization with no backup plan. Perhaps Yellowstone's greatest lesson is humility. For all our technology, we remain at the mercy of forces that shaped this planet long before humans walked it. The same hotspot that fuels Old Faithful's clockwork eruptions could someday rewrite the map of North America. Our task isn't to live in fear, but to respect the power beneath our feet and to build a world resilient enough to withstand its occasional fury. While Yellowstone dominates headlines, another sleeping giant stirs halfway across the world, one with a temper just as fierce but far less famous. New Zealand's Lake Taupo isn't just a scenic wonder, it's the watery lid on a volcanic system capable of unleashing hell. 26,500 years ago, this tranquil blue expanse didn't exist. Instead, the land convulsed in the Oruanui eruption, a cataclysm that ejected 530 cubic kilometers of magma, enough to bury an area the size of New York State under 10 meters of scorching debris. The aftermath reshaped New Zealand's entire North Island, leaving behind a caldera so vast it eventually filled with water, creating the deceptively peaceful lake we see today. What makes Taupo particularly unnerving is its frequency. Unlike Yellowstone's long dormancy, this volcanic zone erupts every few thousand years, and it's overdue. Since Oruanui, Taupo has erupted at least 28 times, with the most recent blast occurring around 230 CE. Maori oral traditions describe that event as the furious outburst of Te-Hota, where fiery clouds turn day into night. Today, the region grumbles constantly. Swarms of tiny earthquakes rattle the area weekly, while the lake's surface occasionally bubbles with volcanic gases. In 2019, GPS sensors detected the ground near Taupo rising by 14 centimeters in just 3 months, a stark reminder that magma still churns below. New Zealand's geological agency, GNS treats Taupo like a coiled serpent. Their monitoring network rivals Yellowstone's with lakebed pressure sensors, airborne gas sniffers, and laser scanners tracking ground deformation in real time. But preparedness here faces unique challenges. Unlike Yellowstone's remote wilderness, Taupo sits at the heart of New Zealand's tourism and agriculture. The lake's shores host vineyards, geothermal power plants, and towns housing tens of thousands. Rotorua, just 80 kilometers north, is a cultural hub for the Maori people. Evacuating these communities would require moving entire populations across a country with limited road networks. Many routes cross active fault lines that could rupture during an eruption. The real wildcard is Topo's style of eruption. While Yellowstone typically explodes violently, Topo sometimes produces effusive eruptions, slower lava flows that give more warning but last for years. The 230C event began with pyroclastic flows racing across the landscape at 600 kilometers per hour, then transitioned into a decade-long lava fountain. Modern disaster models suggest such an event today would blanket Auckland's international airport in ash, crippling New Zealand's economic lifeline. Acid rain could poison the country's famed dairy pastures, while geothermal plumes might disrupt trans-Pacific air traffic for months. Yet in this land of geological peril, resilience runs deep. The Maori, who have lived alongside Topo's tantrums for centuries, weave volcanic awareness into their cultural fabric. School children practice eruption drills alongside earthquake drop and cover routines. Civil defense plans include using Maori traditional meeting grounds as emergency shelters, blending modern science with indigenous wisdom. Even the tourism industry leans into the danger. Boat tours jokingly advertise the world's most unpredictable cruise. Topo's greatest lesson might be its demonstration of living gracefully with inevitable disaster. While we can't prevent supervolcanic eruptions, we can choose whether to fear them or respect them to build societies that bend rather than break when the earth finally speaks again. As the Maori say, Kia hora te marino, may peace be widespread, but beneath that wish lies the unspoken truth their ancestors knew well. Peace is what you carve between the eruptions. The ash-covered streets of Pompeii stand as one of history's most haunting classrooms, a visceral reminder that volcanic fury respects neither wealth nor status. When Mount Vesuvius erupted in 79 AD, it wasn't the sudden explosion that doomed the city, but a cascade of overlooked warnings and human miscalculations. For days before the catastrophe, earthquakes rattled the region common in an area the locals called the home of giants. Springs and wells mysteriously dried up as subterranean shifts blocked water flows. Even the birds seemed to sense impending doom, with historical accounts describing flocks fleeing the mountain days before the eruption. Yet life continued, markets bustled, and frescoes were still being painted in villas when the mountain finally tore itself apart. What makes Pompeii's tragedy so instructive isn't just its scale, estimated at 100 times weaker than Toba's eruption, but its intimacy. Plaster casts of victims frozen in their final moments reveal human stories. A baker still clutching bread loaves, a wealthy family huddled together, even a guard who remained at his post. Their preserved homes show half-eaten meals and hastily abandoned valuables, suggesting many initially survived the eruption's first phase. The real killer was what came next, a pyroclastic surge of superheated gas and ash racing downhill at highway speeds, suffocating everything in its path within seconds. Unlike Toba's slow climate shift, Vesuvius offered no time for adaptation, only instinct. Modern volcanologists pore over Pompeii's ruins like forensic detectives. The stratified ash layers act as a timeline, showing how the eruption unfolded in distinct phases. Early pumice falls allowed some residents to flee, while others perished when roof collapses trapped them indoors. The lesson: not all volcanic hazards are equal. Today's monitoring systems classify eruptions using similar principles, distinguishing between ash plumes, lava flows, and deadly pyroclastic surges, to tailor evacuation plans accordingly. When Mount St. Helens erupted in 1980, for instance, authorities used Vesuvius's case studies to justify their controversial exclusion zone, saving thousands despite public resistance. Yet Pompeii's greatest warning lies in its complacency. The city had weathered smaller eruptions before, fostering a dangerous normalization of risk. Sound familiar? Residents of Naples today live under the shadow of a far larger volcanic threat. Vesuvius remains active, with 3 million people now dwelling in its potential kill zone. Unlike 79 AD, modern sensors dot the mountain slopes, measuring gas emissions and ground swelling with nanometer precision. But technology alone can't overcome human nature. Emergency drills are often poorly attended, while construction projects routinely violate safety zones. Historians note that Pompeii's wealthy had vacation homes along the coast, a luxury escape route most citizens lack. Modern vulnerability maps reveal similar disparities. Affluent neighborhoods often occupy higher, safer ground, while marginalized communities cluster in high-risk valleys. The silver lining is that Pompeii's tragedy birthed the science of volcanology itself. Pliny the Younger's eyewitness account became the first detailed eruption record, coining terms like Plinian column, still used today. His descriptions of the towering ash cloud, like an umbrella pine tree, helped later scientists reconstruct eruption dynamics. Contemporary researchers take this further, using laser scans to model pyroclastic flow paths and virtual reality to simulate evacuation scenarios. One groundbreaking study even analyzed the chemical composition of victims' bones, revealing that many died from thermal shock rather than suffocation, a finding that reshaped modern survival protocols. Perhaps the most profound takeaway is how Pompeii's fate intertwines with Toba's legacy. Both disasters underscore that survival hinges not just on scientific knowledge, but on social cohesion and political will. The skeletons huddled in Pompeii's boat sheds tell us some waited desperately for official rescue that never came. Contrast this with Iceland's 2010 Eyjafjallajökull eruption, where coordinated evacuations and real-time ash tracking prevented a single fatality despite massive disruption. The difference, a culture that treats volcanoes not as mythical monsters but as manageable risks. As we walk Pompeii's stone streets today, we're not just observing history, we're holding a mirror to our own preparedness. The same cognitive biases that blinded ancient Romans to Vesuvius's threat still shape our response to modern dangers, from climate change to pandemics. The ash-preserved grapes on a market stall and the child's toy abandoned in a courtyard remind us that disasters aren't abstract, they're interruptions of ordinary lives. In that sense, Pompeii's legacy isn't a warning about volcanoes alone, but about the fragile thread of human resilience that connects us across millennia. Imagine standing at the edge of Yellowstone's steaming hot springs, knowing that beneath your feet lies enough molten rock to reshape continents. It's a humbling thought, but not as humbling as the realization that humanity might soon have the tools to negotiate with this sleeping giant. Over the past 2 decades, advances in volcano monitoring have transformed from crude seismographs to networks so precise they can detect the ground swelling by less than the width of a grape. Satellites like the European Space Agency's Sentinel-1 constellation now scan Yellowstone weekly with radar, mapping elevation changes down to the millimeter. Infrared sensors aboard NASA Terra satellite track heat anomalies, while drones sample volcanic gases too toxic for humans to approach. This isn't just observation, it's a planetary early warning system unlike anything our ancestors could have dreamed of. One of the most radical proposals comes from an unexpected source, NASA Jet Propulsion Laboratory. In a 2017 study, scientists floated the idea of drilling up to 10 kilometers into Yellowstone's magma chamber, not to trigger an eruption but to prevent one. The concept works like a geothermal power plant in reverse. By pumping water through the boreholes, engineers could gradually cool the magma, siphoning off heat to generate electricity while reducing pressure underground. The numbers are staggering. Such a system might extract enough thermal energy to power nearby cities for thousands of years, all while diffusing the volcanic threat. Critics point out the risks. Drilling could accidentally rupture the chamber's roof, but proponents argue that with careful placement and slow cooling, the benefits might outweigh the dangers. After all, we've already drilled deeper than this for oil. Why not for planetary defense? Yet technology's greatest role may lie in buying time rather than stopping eruptions entirely. In New Zealand, researchers are testing artificial intelligence that can predict volcanic activity months earlier than traditional methods. By analyzing decades of seismic data, these algorithms spot subtle patterns humans miss, tiny tremors that precede major events like breadcrumbs leading to disaster. Similar systems in Iceland now link directly to civil defense networks, triggering automated alerts when sensors detect unusual gas emissions or ground movement. The goal isn't just accuracy, but speed. During the 2021 Fagradalsfjall eruption, such systems gave Reykjavik residents 40 minutes warning before ash clouds reached the city, precious time to seal windows or retrieve asthma inhalers. The wild card in all this preparation, social science. Volcanologists now work alongside psychologists to understand why people ignore evacuation orders, even with overwhelming evidence of danger. Studies show that communities with first-hand eruption experience, like those near Indonesia's Merapi volcano, respond faster to warnings than those relying on abstract risk maps. This has led to innovative outreach. In Naples, schoolchildren take virtual reality field trips through Vesuvius's crater, while Mexican villages near Popocatépetl participate in annual evacuation races, turning preparedness into a festival. The lesson is clear: technology alone won't save us unless people trust and understand it. Perhaps the most sobering realization is that for all our advances, nature still holds the upper hand. In 2020, a surprise eruption at New Zealand's Whakaari volcano killed 21 people despite intensive monitoring, a reminder that volcanoes don't always follow rules. Yet even in failure, there's progress. Post-disaster analysis revealed that Whakaari's warning signs were there, just misinterpreted. Now, machine learning models trained on that tragedy do better. It's a pattern repeated throughout history. Each eruption, each near miss, sharpens our tools for the next one. The race between human ingenuity and geological fury isn't one we can win outright. But with every sensor deployed, every algorithm refined, we're learning to run faster. Whether it's enough remains to be seen. What's certain is that for the first time in Earth's history, one of its inhabitants is looking the volcano in the eye and daring to plan a countermove. The relationship between climate change and volcanic activity might seem like science fiction, but the evidence is etched into Earth's geological record. Picture this: as glaciers retreat under rising temperatures, their colossal weight lifts from the planet's crust like a giant stepping off a trampoline. This decompression can destabilize magma chambers below, potentially awakening sleeping volcanoes. Iceland offers a stark case study. Its volcanic activity increased sharply as its ice sheets melted after the last ice age. Research published in the journal Geology found that eruptions there became up to 100 times more frequent as glacial cover shrank between 12,000 and 4,500 years ago. The reason: reduced pressure allows magma to expand and rise more easily, like uncorking a shaken bottle of soda. But the connection isn't just ancient history. In 2020, a study of Alaska's Mount Edgecumbe revealed something startling. The long-dormant volcano was showing signs of reawakening, with seismic activity and ground uplift linked to nearby glacier melt. Similar patterns have been noted in the Andes and the Cascades, where shrinking ice caps correlate with increased volcanic tremors. The mechanics are complex. As ice vanishes, the crust rebounds, fracturing rock and creating pathways for magma. It's not just about pressure changes. Melting glaciers also alter groundwater flow, which can interact with magma to trigger explosive steam-driven eruptions. Critics caution against oversimplifying the link. Volcanic systems operate on timescales far longer than human-recorded climate data, making cause and effect tricky to pin down. Some argue that while deglaciation might accelerate eruptions, it doesn't necessarily create new volcanoes, just hastens the inevitable. Others point out that not all regions respond the same way. Antarctica, for instance, has seen massive ice loss with no notable uptick in volcanic activity. Yet, the difference may lie in local geology. Volcanoes fed by thick continental crust could be less sensitive to surface changes than those in thin, brittle zones like Iceland. The real wildcard is feedback loops. A major eruption like Toba's can inject so much sulfur dioxide into the atmosphere that it cools the planet for years, potentially regrowing glaciers that then suppress volcanic activity again. It's a planetary thermostat with a dangerous delay. By the time the cooling effect kicks in, countless eruptions may already be underway. Climate models now incorporate these interactions, revealing how a warming world might unintentionally unlock geological hazards. What does this mean for the future? Imagine a scenario where melting ice in Greenland triggers more frequent Icelandic eruptions, whose ash clouds disrupt global air travel, while also spewing greenhouse gases that amplify warming. Or consider the Alaskan volcanoes currently buried under ice. If they awaken, their eruptions could release methane trapped in permafrost, accelerating climate change further. The stakes are highest in densely populated regions like the Pacific Ring of Fire, where millions live in the shadow of volcanoes that might react unpredictably to shifting climate pressures. The takeaway isn't doom, it's preparation. Scientists are now developing early warning systems that monitor both glacial retreat and volcanic unrest, pairing satellite data with ground sensors. In Chile, researchers are mapping how shrinking glaciers might affect the Laguna del Mar volcanic field, a potential hotspot for future activity. Meanwhile, policymakers are starting to treat geological climate risks as seriously as rising seas or wildfires. After all, if the past teaches us anything, it's that Earth systems are deeply intertwined, and ignoring those connections could leave us blindsided when the ground beneath our feet decides to speak. The ash-choked skies and frozen landscapes after Toba's eruption didn't just test human survival. They may have rewritten the map of our species' journey across the planet. Geneticists tracing the branches of our family tree have uncovered a curious pattern. Around 74,000 years ago, the small bands of humans who endured the volcanic winter began fanning out from Africa with newfound urgency. This wasn't a leisurely migration, it was a desperate search for livable land, driven by a climate catastrophe that turned familiar territories hostile. One clue lies in the mitochondrial Eve theory, which traces all modern humans back to a single African ancestor who lived roughly 200,000 years ago. For millennia, our ancestors remained largely confined to the continent's warmer regions. But after Toba, something changed. Genetic markers show populations splitting into distinct groups, some venturing along coastlines toward Asia, others following river valleys into Europe. The timing aligns eerily with the eruption's aftermath, as if the volcanic winter acted like a cosmic push, propelling humanity toward every corner of the globe. Archaeological finds paint a similar picture. In India's Jharu Valley, stone tools appear both above and below the Toba ash layer, but with a striking difference. The post-eruption tools are smaller, more refined adaptations for hunting smaller game as forests gave way to grasslands. Further east, in what's now Malaysia, cave deposits reveal human occupation shortly after Toba, with evidence of shellfish harvesting that suggests coastal routes were lifelines. These scattered breadcrumbs form a trail of resilience, showing how survivors adapted their technologies and strategies to thrive in a world remade by disaster. The real revelation comes when we piece together climate models with migration routes. As Toba's aerosols cooled the tropics, equatorial regions may have become more habitable than the frozen north. Some researchers propose a blue highway theory, that early humans followed shorelines where marine resources buffered them from collapsing terrestrial ecosystems. Shell middens in South Africa's Pinnacle Point caves support this, showing continuous occupation through the volcanic winter thanks to a diverse diet of seafood, plants, and small game. Meanwhile, pollen records from Southeast Asia suggest rainforests rebounded quickly after the eruption, creating green corridors that beckoned migrants eastward. But here's the twist: not all paths were about escape. Some movements may have been strategic. In the Levant, where Neanderthals and humans overlapped, Toba's cooling could have temporarily tilted the balance in our favor. With Neanderthals adapted to colder climates, the sudden deep freeze might have pushed them south only to collide with human groups expanding northward as African habitats deteriorated. The resulting competition could explain why human genetic diversity shows signs of intense selection pressure around this time, as only the most adaptable lineages survive. What emerges isn't just a story of survival, but of opportunity. The same catastrophe that nearly erased humanity also cleared ecological space for innovation. With megafauna dwindling, those who mastered flexible hunting strategies and broad diets gained an edge. Coastal migrants developed fishing technologies that later enabled island hopping across Southeast Asia. Others honed social networks to share scarce resources, a skill that would prove invaluable when colonizing unfamiliar continents. The ultimate irony. Toba's devastation may have been the crucible that forged traits we now consider quintessentially human: ingenuity, cooperation, and restless curiosity to explore beyond the horizon. Every time you meet someone from a distant culture or trace your ancestry across continents, you're witnessing the legacy of that ancient exodus, a journey begun when the world turned to ash and our ancestors chose to walk toward the dawn. The aftermath of Toba's eruption didn't just reshape human destiny, it rewrote the entire playbook of life on Earth. As ash blotted out the sun and temperatures plummeted, ecosystems faced a brutal triage. Tropical rainforests, once teeming with biodiversity, withered into skeletal remains, grasslands froze into barren tundras, and freshwater systems turned toxic under relentless acid rain. For megafauna like the towering woolly mammoths or the saber-toothed cats, the sudden loss of vegetation triggered a domino effect. Starving herbivores meant starving predators. Fossil records from this period reveal eerie gaps, like missing chapters in nature's diary. In Southeast Asia, entire species of giant primates vanished, while North America's dire wolves and giant ground sloths clung to existence by the thinnest of threads. Yet amid this devastation, nature's survivors wrote their own epic of resilience. Smaller, generalist species creatures like rats, crows, and cockroaches prospered where specialists faltered. Their secret: versatility. While mammoths required vast grasslands, a rat could subsist on seeds, insects, or even human refuse. Birds with varied diets, like ravens, outlasted those dependent on specific plants or prey. Even some large predators adapted. Wolves, for instance, shifted from hunting mega herbivores to scavenging smaller carcasses, a flexibility that carried their lineage into the modern era. These weren't just random survivors, they were the ultimate opportunists, shaped by catastrophe into the ecological winners of a new world. The volcanic winter also accelerated evolutionary quirks that still echo today. Take the cheetah. Genetic studies show all living members descend from a handful of individuals who survived Toba's aftermath, leaving the species with such low diversity that even distant relatives are nearly identical. Similar bottlenecks appear in tigers, giraffes, and even certain tree species. This genetic bottleneck effect isn't just a historical curiosity, it's a warning. Modern conservationists use these ancient patterns to predict which endangered species might lack the diversity to adapt to climate change or habitat loss. A cheetah's struggle 74,000 years ago mirrors the plight of today's snow leopards or rhinos, reminding us that extinction isn't always a single event, but a slow erosion of resilience. What's truly astonishing is how quickly life rebounded once the ash settled. Pollen samples from lake sediments tell a story of ecological amnesia within decades. Pioneer species like ferns and mosses colonized the wastelands, stabilizing soils for forests to return. Insects, those masters of metamorphosis, repopulated faster than larger animals, their short lifespans allowing rapid adaptation. Even the ocean saw surprises. Coral reefs that survived in deep, thermally stable pockets became the founders of new colonies, their genetic legacy still visible in today's vibrant ecosystems. This rebound wasn't just survival, it was reinvention. The lesson for our modern biodiversity crisis: catastrophe isn't necessarily the end, it's a harsh editor. The species that endured Toba's wrath did so through a mix of luck, plasticity, and sometimes sheer grit. As we face our own planetary challenges, deforestation, climate shifts, pollution, we're witnessing a similar winnowing. The difference this time: humanity isn't just a bystander. We're both the force disrupting ecosystems and the stewards who can steer their recovery. The fossils of Toba's victims whisper a sobering truth: extinction is forever. But the descendants of its survivors prove that when nature's resilience is met with human ingenuity, even the darkest winters can give way to spring. Could a supervolcano erupt again? The terrifying answer is yes, it's only a matter of time. Earth's geological clock doesn't tick to human schedules, but the numbers don't lie. Over the past 2.5 million years, supereruptions have occurred roughly every 50 to 100,000 years. The last one, Toba, was 74,000 years ago. By that math, we're statistically overdue. But here's the twist: volcanoes don't punch time cards. Yellowstone's 3 catastrophic eruptions spanned intervals of 600,000 and 700,000 years. No neat pattern, just the slow buildup of pressure until the Earth can't contain it any longer. What makes this uncertainty so unsettling is the sheer power lurking beneath our feet. Right now, beneath Yellowstone's geysers, a magma chamber the size of Rhode Island simmers at temperatures hot enough to melt rock. Similar time bombs tick under New Zealand's Lake Taupo and Indonesia's Lake Toba itself, proof that these aren't extinct monsters, just sleeping ones. Scientists monitoring these regions have detected unsettling signs: swarms of tiny earthquakes, ground inflation measured in centimeters, and spikes in geothermal activity. None guarantee an imminent eruption, but they're reminders that these systems are alive and restless. The real challenge isn't just predicting the next eruption, it's surviving it. Modern civilization has no precedent for an event that could blot out the sun for years. Agricultural systems dependent on predictable seasons would collapse under endless winter. Global supply chains, already fragile, would snap under the strain of ash-clogged ports and grounded flights. Even our digital infrastructure faces threats. Volcanic ash carries an electrostatic charge capable of short-circuiting power grids, as seen in minor eruptions like Iceland's 2010 Eyjafjallajökull event. That disruption, though temporary, cost the global economy nearly $5 billion. A super-eruption's toll would be unimaginable, yet there's reason for cautious optimism. Unlike our ancestors, we're not blind to the threat. Satellite networks track ground deformation in real time, while supercomputers model eruption scenarios with startling accuracy. NASA experimental plans to cool Yellowstone's magma chamber might sound like science fiction, but geothermal energy projects in Iceland have already proven we can harness volcanic heat safely. More crucially, international collaborations like the Global Volcanism Program share data across borders, ensuring no warning signs go unnoticed, preparing for the inevitable means rethinking how we build resilience. Seed vaults in Norway and elsewhere preserve genetic diversity for post-catastrophe agriculture. Cities near volcanic zones are drafting evacuation plans that account for ashfall meters thick, not just centimeters. Even everyday technologies, from air filtration systems to ash-resistant drones, could become lifelines when the skies darken. The goal isn't to live in fear, but to respect the Earth's power and match it with our ingenuity. The haunting truth is this: supervolcanoes have shaped our past and will shape our future. But for the first time in history, we're not just potential victims, we're students of the threat, armed with knowledge our ancestors could only dream of. Whether that's enough to tip the scales remains the ultimate test of human adaptability. The clock is ticking, but it hasn't run out yet. Deep in the caves of Europe and the rock shelters of Africa, our ancestors left behind clues etched in ochre and charcoal, not just images of animals and hunters, but something far more haunting. Around the time Toba's ash settled across the globe, a shift appears in prehistoric art. Gone are the serene depictions of solitary bison or graceful antelope. In their place emerge chaotic compositions, animals with twisted limbs, humanoid figures caught in what looks like flight or falling, zigzagging lines that evoke lightning or perhaps the shuddering earth itself. To modern eyes, these scenes feel less like leisurely decoration and more like primal screams frozen in stone. One of the most striking examples comes from Indonesia itself, not far from Toba's epicenter. In the limestone caves of Sulawesi, hand stencils dating back 44,000 years share cave walls with bizarre hybrid creatures, part human, part beast, locked in violent struggle. While these paintings postdate Toba by millennia, anthropologists note a fascinating pattern. The older the art, the more it leans toward abstraction and turmoil. Could this be cultural memory passed down through generations? A subconscious echo of the catastrophe that reshaped their world? The trauma hypothesis gains traction when examining global patterns. In South Africa's Blombos Cave, archaeologists uncovered 73,000-year-old engravings, precise crosshatch designs etched into ochre fragments. What makes these markings extraordinary isn't just their age, but their timing. They appear within centuries of Toba's eruption, as if the act of creation itself became a lifeline amidst chaos. Similar symbols emerge across continents. Spirals in Australian rock art that mirror volcanic whirlwinds, Spanish cave paintings where herds of animals stampede beneath jagged red lines resembling fiery skies. Not all scholars agree on a direct link to Toba. Some argue that art naturally evolves toward complexity, or that surviving pieces simply reflect the durability of certain pigments. Yet even skeptics acknowledge the psychological toll such an event would have taken. Imagine generations raised under ashen skies, their oral traditions filled with tales of a time when the sun vanished and the ground trembled. Art may have served as both communal therapy and survival manual, a way to process collective trauma while encoding critical knowledge, those zigzagging lines. They might represent migration routes around newly formed lava fields, the hybrid creatures, possibly spirit guides to navigate a world where normal rules no longer applied. The most poignant evidence comes from children. In France's Chauvet Cave, tiny footprints preserved in soft clay show where young ones accompanied adults deep underground, their small hands adding to the swirling murals. These intimate traces suggest art wasn't just ritual, it was education. In flickering torchlight, elders may have used these images to teach which plants grew after fires, where to find water when rivers turned toxic, or how to read the changed behaviors of prey animals. The caves became sanctuaries of memory where survival strategies were literally drawn from experience. What emerges is a radical idea that human creativity didn't just persist through catastrophe, it was forged by it. The same cognitive flexibility that let our ancestors adapt their tools and diets may have found its purest expression in these early artworks. When the external world became unpredictable, turning inward to shape color and form became a way to reclaim agency. Every stroke of pigment was an act of defiance against randomness, a declaration that even in a broken world, meaning could be made. This legacy lives on in our brains today. Neuroimaging shows that creating art activates the same neural pathways associated with problem solving and emotional regulation. The urge to depict our fears and hopes didn't begin with modern galleries. It began in smoke-filled caves, where the first storytellers used the walls as canvases to process what no words could yet describe. The next time you see a child's drawing of a storm or a darkened sun, you might be glimpsing an unbroken thread stretching back to Toba, proof that even in the face of annihilation, the human spirit's response has always been to create. Food scarcity after Toba's eruption wasn't just a challenge, it was a daily battle against extinction. With forests reduced to skeletal remains and large game vanishing, our ancestors faced a grim calculus: adapt their diets or perish. Archaeological sites from this period tell a story of radical culinary flexibility. In South Africa's Pinnacle Point caves, researchers uncovered burnt shells from mussels and limpets mixed with charred plant remains, proof that coastal foraging became a lifeline when terrestrial ecosystems collapsed. These weren't casual meals, they were acts of desperation and ingenuity as survivors turned to the sea's unpredictable bounty while the land lay barren. The shift from megafauna to smaller prey left its mark on tools and tactics. Gone were the heavy spears designed for mammoths or giant deer. In their place emerged lighter, more versatile implements, delicate blades for processing nuts and roots, finely sharpened projectile points for hunting rabbits or birds. At India's Jewalapuram site, stone tools found above the Toba ash layer show a striking reduction in size, optimized for precision over power. This wasn't just a change in technology, it reflected a fundamental rethinking of survival. When a single missed hunt could mean starvation, efficiency became paramount. Some anthropologists even speculate that the bow and arrow, a game changer for hunting elusive small game, may have its roots in this era of scarcity. But the most revolutionary adaptations may have been social. Scattered bands that once competed for dwindling resources began cooperating in unprecedented ways. Evidence from Kenyan sites suggests the emergence of trade networks spanning hundreds of kilometers, obsidian flakes traced to distant quarries, shells transported far inland. These exchanges weren't mere commerce, they were insurance policies against localized famine. If one group's territory had edible tubers and another's held productive fishing spots, sharing knowledge and goods could mean the difference between life and death. The very concept of reciprocity may have been forged in these hungry years, laying the groundwork for complex human societies. Perhaps the most contentious theory involves agriculture's shadowy beginnings. While full-scale farming wouldn't emerge for millennia, some researchers point to tantalizing clues of proto-cultivation. In New Guinea's highlands, microscopic traces of taro starch on 70,000-year-old grinding stones suggest deliberate plant processing. Similarly, wild cereal grains found in Jordan's Azraq Basin show signs of selective harvesting around the same period. These weren't cultivated fields as we know them, but rather the first hesitant steps toward manipulating food sources, a survival strategy born from necessity. The legacy of this culinary revolution lingers in our bodies today. Genetic studies reveal that populations who endured Toba's aftermath developed enhanced abilities to metabolize diverse plant starches and marine fats adaptations that allowed them to extract maximum nutrition from meager diets. Even our taste preferences might carry echoes of that time. The human fondness for umami-rich foods like mushrooms and fermented meats may stem from their high caloric value in a world where every bite counted. What's truly remarkable isn't just that our ancestors found enough calories to survive, but how they transformed scarcity into innovation. The same crisis that erased traditional food sources forced experimentation with new ones, from shellfish to insects, from bitter tubers to toxic nuts rendered edible through ingenious processing. This wasn't just survival, it was the birth of human gastronomy, a testament to our species' ability to turn desperation into creativity. The next time you enjoy a meal, remember, you're tasting the legacy of history's hungriest survivors. The psychological scars left by Toba's eruption would have run far deeper than the ash layers it deposited across continents. Imagine generations born beneath perpetually gray skies, their world reduced to a monochrome landscape where the sun was a fading memory. For modern researchers studying disaster psychology, this scenario isn't just theoretical, it's a window into how trauma reshapes societies. Studies of communities surviving volcanic eruptions like Mount Pinatubo in 1991 reveal haunting parallels. Survivors describing the disorientation of perpetual twilight, the primal fear of unstable ground, and the grief for landscapes that vanished overnight. These aren't fleeting reactions, but imprints that linger for decades, passed down through collective memory. One of the most profound coping mechanisms may have been the birth of communal storytelling. In the absence of written language, oral traditions became living archives of survival. The Aboriginal Australian legend of the rainbow serpent, a creator being who brings both destruction and renewal, bears striking resemblance to volcanic events, with its descriptions of roaring earth and fiery devastation. Similarly, the Klamath people's tale of the underworld spirit Lau mirrors the eruption of Mount Mazama with eerie accuracy. These myths serve dual purposes, preserving practical knowledge about geological hazards while offering psychological catharsis. By framing catastrophe within a narrative of cosmic balance, destruction preceding rebirth, our ancestors transformed helplessness into meaning. Neurobiology offers another clue to humanity's resilience. Brain scans of modern disaster survivors show heightened activity in regions associated with pattern recognition and social bonding. Faced with unpredictable environments, the human mind becomes hyper-alert to potential threats while simultaneously strengthening tribal affiliations. This neurological double helix, vigilance plus unity, may explain the explosion of symbolic artifacts after Toba. Beads made from ostrich eggshells in Africa, intricate bone carvings in Europe. These weren't mere decorations. They were social glue, tangible proof of shared identity in a shattered world. When survival hinges on cooperation, creating and exchanging symbolic objects becomes a way to reinforce trust across scattered bands. Yet trauma leaves fractures alongside resilience. Anthropologists studying post-eruption burial sites note disturbing patterns. Skeletons with signs of repetitive stress injuries from overwork, graves of children with unusually high rates of malnutrition. The psychological toll surfaces in more subtle ways too, the abrupt disappearance of certain art styles, as if cultural knowledge was lost too quickly to transmit. At Tanzania's Mamba Cave, tool-making traditions that had persisted for millennia suddenly simplify after Toba's timeline, suggesting a breakdown in teaching networks. Disaster didn't just test physical survival, it threatened the very continuity of culture. The most poignant evidence of psychological adaptation comes from what changed in how humans treated their dead. In Israel's Kafse Cave, burials from before the volcanic winter show simple pit graves, but later interments reveal elaborate rituals, ochre pigment scattered over bodies, grave goods like flint tools placed carefully alongside remains. This shift suggests something profound. Confronted with mortality on an unprecedented scale, survivors began venerating the dead as a way to anchor themselves in time. Grief rituals became time capsules, ensuring that even if individuals perished, their memory and the lessons they carried would endure. What emerges is a portrait of humanity's mind under siege, not just enduring, but transmuting suffering into the foundations of civilization. The same catastrophe that nearly erased us may have forged our capacity for abstract thought, complex social structures, and artistic expression. Modern therapy techniques like narrative exposure therapy, where survivors reframe trauma as part of a larger life story, echo these ancient coping strategies. The lesson isn't just that we survived, but that we rewired our very cognition to turn catastrophe into a crucible for creativity. When the skies finally cleared after Toba's long winter, what emerged wasn't just a species clinging to existence. It was one poised to paint on cave walls, chart the stars, and ultimately unravel the mysteries of the volcano that reshaped its soul. Volcanoes and asteroids may seem like entirely different beasts, one born from Earth's fiery depths, the other a visitor from the void. But when it comes to reshaping life on our planet, they share a terrifying kinship. The asteroid that struck 66 million years ago unleashed energy billions of times greater than Toba's eruption, leaving a crater 150 kilometers wide under what's now Mexico's Yucatan Peninsula. That single impact triggered wildfires across continents, acidified the oceans, and blotted out the sun for years, erasing 75% of all species, including the mighty dinosaurs. Compared to this, Toba's devastation seems almost modest. Yet here's the paradox: while the dinosaur-killing asteroid cleared the stage for mammals to rise, Toba's eruption nearly erased the star performance. Scale isn't just about raw power, it's about precision. The Chicxulub asteroid struck with the subtlety of a sledgehammer, its effects indiscriminate and global. Toba, by contrast, was more like a scalpel. Its volcanic winter lasted decades rather than millennia, and its deadliest blows were targeted. Tropical ecosystems suffered most, while some temperate regions rebounded faster. This selectivity created evolutionary bottlenecks not just for humans but for other species too. Genetic studies show cheetahs, tigers, and even certain rice varieties share our telltale lack of diversity, all tracing back to the same period of crisis. The dinosaurs faced annihilation. Our ancestors faced curation, a brutal filtering that favored adaptability over brute strength. What truly sets Toba apart isn't its place in Earth's hierarchy of disasters, but its role as a mirror. The Permian-Triassic extinction 252 million years ago, nicknamed the Great Dying, wiped out 96% of marine life through millennia of volcanic eruptions far larger than Toba. But those eruptions didn't just alter ecosystems. They transformed Earth's very chemistry, acidifying the oceans until shells dissolved mid-formation. Toba's aftermath, while severe, never approached that level of planetary rewiring. Yet for early humans, the stakes couldn't have been higher. Unlike the Permian's mindless trilobites or the Cretaceous's instinct-driven dinosaurs, we faced disaster with something new: culture. The same cognitive gifts that let us craft tools and share knowledge became our lifeline, not just to survive, but to document, to learn, to ensure the next generation wouldn't face the darkness unprepared. Modern climate science offers a sobering lens to compare these events. The asteroid impact caused global temperatures to plummet by as much as 20 degrees Celsius, a deeper freeze than Toba's 10-degree drop. But duration matters as much as intensity. While the asteroid's winter lasted perhaps a decade, its cascading effects collapsed food chains, lost biodiversity echoed for millions of years. Toba's disruption, though shorter, struck during a critical crossroads in human evolution. Had it erupted 100,000 years earlier, before our ancestors developed complex language and social networks, we might have shared the fate of other hominids like Homo erectus, who vanished around this time. Timing made Toba not just a disaster, but a Darwinian exam, one that tested whether our species' burgeoning intelligence could outwit the planet's fury. The most humbling lesson lies in Earth's resilience. After the asteroid, ferns dominated the scorched landscape within years, nature's first responders. Post-Toba, grasslands expanded where forests fell, creating new opportunities for adaptable survivors. Our planet doesn't just endure catastrophes, it repurposes them. The same volcanic soils that choked the skies became fertile grounds for rebirth. This cyclical rhythm puts human crises in perspective, from pandemics to climate change. The question isn't whether life will continue, but what form it will take. The dinosaurs never saw their doom coming. Our ancestors not only saw Toba's aftermath, but decoded its lessons, turning survival into strategy. That's the real measure of a disaster's scale, not just the damage it inflicts, but the wisdom it leaves in its wake. Right now, beneath the serene landscapes of Yellowstone and the tranquil waters of Lake Taupo, an invisible war is being waged, not against the supervolcanoes themselves, but against uncertainty. The United States Geological Survey, alongside global partners like UNESCO International Geoscience Program, operates a vast, high-tech sentinel network designed to catch the slightest whisper of unrest. Picture this: hundreds of seismometers buried in the earth like delicate stethoscopes, listening for the faintest heartbeat of magma movement. Gas sensors perched near fumaroles sniff the air for spikes in sulfur dioxide, a potential harbinger of rising molten rock. And orbiting high above, satellites like the European Space Agency's Sentinel-1 peer down with radar eyes, measuring ground inflation to the millimeter. This isn't just science, it's a planetary early warning system forged from the lessons of Toba's near-extinction event. The real magic lies in how these systems collaborate. When sensors at Yellowstone's Norris Geyser Basin detect unusual tremors, data funnels instantly to the USG's Yellowstone Volcano Observatory in Colorado, where algorithms compare the patterns to centuries of eruption precursors. Similar hubs in New Zealand, Italy, and Japan form a global neural network, sharing insights across borders. In 2022, this cooperation proved its worth when a swarm of earthquakes beneath Italy's Campi Flegrei, a supervolcano dwarfing Vesuvius, triggered automated alerts across Europe. Within hours, scientists from 6 countries were analyzing the signals, ruling out imminent danger but tightening monitoring. Such coordination means that unlike our ancestors, we wouldn't face a super eruption blindfolded. Yet technology alone isn't enough. The human element remains irreplaceable. At monitoring stations like Hawaii's Hawaiian Volcano Observatory, volcanologists practice a peculiar blend of cutting-edge analysis and old-school intuition. They track the subtle lengthening of cracks in the earth, note changes in the pitch of geothermal vents, even observe animal behavior, an echo of ancient traditions where birds fleeing a mountain signaled danger. Modern tools amplify these observations. Drones equipped with infrared cameras map heat gradients invisible to the naked eye, while AI models trained on millennia of eruption data predict scenarios with eerie accuracy. The goal isn't to stop an eruption that's beyond our power, but to buy time. Early warnings could allow evacuations from high-risk zones, protect critical infrastructure, and stockpile food reserves before ash clouds paralyze transportation. The stakes couldn't be higher. A 2018 study modeled a Yellowstone eruption's economic impact, estimating global losses exceeding $3 trillion in the first year alone. Air travel would cease as abrasive ash shredded jet engines, while power grids from Chicago to Copenhagen might fail under the weight of conductive particles. But here's the hopeful twist: we're no longer passive observers. Projects like NASA's Earth Surface Mineral Dust Source Investigation track how volcanic aerosols disperse, helping farmers prepare for darkened skies. Seed banks in Norway and Kenya preserve crop diversity against agricultural collapse. Even financial systems are adapting. The World Bank now includes supervolcanic eruptions in its catastrophic risk models, ensuring insurance mechanisms exist to rebuild. What's truly revolutionary is how this vigilance reshapes our relationship with these sleeping giants. No longer mythical forces of capricious gods, supervolcanoes are becoming calculable risks, their rhythms decoded, their threats quantified. The same satellites that monitor magma chambers also track illegal deforestation and carbon emissions, proving that protecting humanity from nature's fury goes hand in hand with protecting nature from ours. When the next supervolcano stirs, we may not be able to silence its roar, but for the first time in Earth's history, its children will be listening. Could we weather a super eruption today? On paper, our odds look stronger than our ancestors. Satellites track ground deformation in real time. Global food reserves could theoretically buffer shortages, and medical advances might mitigate respiratory crises from ash inhalation. Imagine drones mapping safe evacuation routes through ash-choked skies, or international coalitions airlifting supplies to disaster zones. When Indonesia's Mount Tambora erupted in 1815, a mere fraction of Toba's power, it triggered the infamous year without summer, collapsing crops across Europe and North America. Today, hydroponic farms and lab-grown meat could theoretically bypass sun-starved fields, while geoengineering proposals suggest injecting reflective particles to counteract volcanic cooling, a modern twist on nature's own sulfurous haze. Yet technology alone can't erase vulnerability. Our interconnected world spins on fragile threads. A single season of failed harvests in the American Midwest and Ukrainian breadbaskets would ripple through global markets, emptying supermarket shelves from Tokyo to Toronto. The 1883 Krakatoa eruption demonstrated how volcanic ash can disable electrical grids. Imagine that scenario playing out across continents, with transformers exploding under conductive ashfall and hospitals losing power. Political scientist Brian Toon modeled a Yellowstone eruption's aftermath, predicting mass migrations as ash renders the Great Plains uninhabitable, potentially triggering conflicts over dwindling arable land. Even with stockpiled grain, distribution would become a nightmare. Truck convoys stalled by zero visibility, rail lines buried under meters of abrasive powder, and air transport grounded indefinitely. The real wild card isn't just physical infrastructure, but social cohesion. Disaster anthropologists studying Hurricane Katrina and the Fukushima nuclear crisis found that pre-existing inequalities magnify catastrophes. Elderly populations might struggle to evacuate ash-choked cities, while marginalized communities often occupy floodplains where ash mixes with rain into deadly cement like slurries. Historical precedents offer grim warnings. The 1783 Laki eruption in Iceland poisoned livestock with fluoride, leading to famine that killed 20% of the population, not from the eruption itself, but from the societal collapse that followed. Modern insurance systems and disaster relief might buffer the initial blow, but prolonged disruption could test the limits of even robust democracies. Preparation is where hope glimmers brightest. Japan's meticulous earthquake drills and Iceland's volcanic response protocols prove that societies can cultivate resilience. On an institutional level, NASA and the United Nations Office for Disaster Risk Reduction now run supervolcano preparedness simulations, stress-testing supply chains and communication networks. Grassroots movements take inspiration from indigenous knowledge. The Maori in New Zealand maintain ancestral evacuation routes around Lake Taupo, while Filipino communities near Mayon volcano practice centuries-old ash farming techniques to restore soil fertility. Technological solutions like ash-resistant drones and portable water filters emerge from these cross-cultural exchanges, blending innovation with tradition. Ultimately, survival hinges on recognizing supervolcanoes as shared adversaries rather than distant curiosities. When Mount Pinatubo erupted in 1991, international scientific cooperation and preemptive evacuations saved tens of thousands, proof that unity can temper disaster. The same satellites monitoring Yellowstone also track climate change and deforestation, reminding us that planetary threats demand planetary responses. Our ancestors endured Toba's winter through adaptability and cooperation. We must honor that legacy by building systems flexible enough to bend without breaking when the Earth next reminds us of its power. When disaster strikes on a global scale, survival isn't just about geology, it's about justice. Picture this: ash clouds blanket the skies, crops fail worldwide, and suddenly, stockpiles of food, medicine, and clean water become the most precious commodities on Earth. Who gets priority when resources shrink to a fraction of what's needed? History offers grim precedents. During the 1918 flu pandemic, wealthier nations secured vaccines first, leaving vulnerable populations exposed. In a supervolcano winter, the stakes would be exponentially higher. Would vaccines, air filters, or heat-resistant seeds flow to those most at risk, or to those who could pay the most? The ethical quagmire deepens when you consider that the nations least responsible for climate change, often poorer countries near the equator, might ironically become the most habitable zones as temperatures plummet. Migration would spark another moral crisis. Borders, already contentious in peaceful times, could become flashpoints for conflict. When Indonesia's Mount Tambora erupted in 1815, famine-driven riots erupted across Europe. Now imagine that scenario with modern population densities and armed borders. Would countries with stable climates accept millions of climate refugees or seal their borders with force? Iceland's handling of volcanic threats offers a glimpse of one approach. Their civil defense plans include repurposing schools and community centers as emergency shelters. But scaling this goodwill globally, where resources are unevenly distributed, would require unprecedented international cooperation. Maintaining order presents its own ethical labyrinth. Martial law might seem inevitable, but at what cost to civil liberties? After Hurricane Katrina, law enforcement faced criticism for prioritizing property protection over rescue operations in marginalized neighborhoods. In a years-long volcanic winter, governments might ration fuel, restrict movement, or even mandate labor for essential farming. The balance between survival and freedom would test democracies to their core. Philosophers like John Rawls argued that just societies should prioritize the least advantaged, but in practice, power often flows toward those who already have it. Technology could either exacerbate inequalities or bridge them. Vertical farms and geothermal energy might keep some cities functioning, but if these solutions are only available in wealthy nations, they could widen the gap between haves and have-nots. Conversely, open-source designs for ash-resistant water filters or low-cost greenhouse kits could democratize survival. The choice hinges on whether we view crisis as a zero-sum game or a collective challenge. Perhaps the most profound question isn't logistical, but philosophical. What kind of civilization do we want to be when the sky darkens? The survivors of Toba didn't have the luxury of choice. Their world shrank to the immediate struggle for food and warmth. We, however, have the rare chance to preemptively answer these ethical dilemmas. From United Nations frameworks for disaster equity to community-led resilience networks, the tools for a just response exist. The only uncertainty is whether we'll use them, or wait until the ash falls to decide who deserves a place in the sunlight. Humanity's survival after Toba wasn't just luck, it was a masterclass in resilience written in the language of bones, tools, and shared firelight. In the shadow of endless winter, our ancestors didn't merely endure, they reimagined what it meant to be human. Take the caves of South Africa's Pinnacle Point, where archaeologists uncovered seashells meticulously crafted into beads alongside ochre pigments, evidence of symbolic expression emerging amidst scarcity. These weren't just decorations, they were social currency, a way to bind scattered groups together when isolation meant extinction. The act of creating beauty in a broken world may have been our first declaration that survival wasn't enough, we needed meaning too. Cooperation became our secret weapon. Genetic studies reveal a fascinating pattern. Populations that weathered Toba's aftermath show markers for increased oxytocin receptors, the so-called trust hormone linked to social bonding. This biological echo suggests that catastrophe didn't turn us inward, it compelled us to reach out. Archaeological sites from this period show unprecedented trade networks spanning hundreds of kilometers. Obsidian flakes from distant quarries turn up in coastal caves, while marine shells appear deep inland, proof that survival hinged on interdependence. When the skies darkened, our ancestors didn't hoard, they bartered, shared, and in doing so, wove the first threads of global connection. Innovation flourished in unexpected ways. The same volcanic ash that smothered landscapes also became a tool, literally. At India's Jharu Valley, stone tools found above the Toba layer show a clever twist. Artisans began mixing crushed volcanic glass with resin to create super-adhesive grips for spearheads. This wasn't just practicality, it was ingenuity born of necessity. Elsewhere, the scarcity of large game led to revolutionary hunting technologies. The earliest evidence of bow and arrow use appears in Sri Lankan caves dated to shortly after Toba, a silent testament to how pressure breeds invention. But perhaps the most profound legacy lies in how the catastrophe reshaped our minds. Cognitive archaeologists point to a surge in abstract thinking during this period. The Blombos cave engravings' precise geometric patterns etched into ochre demonstrate a leap in symbolic reasoning. Some researchers argue that Toba's environmental chaos demanded new levels of planning and foresight. Tracking migrating herds or predicting seasonal changes in a climate gone mad required mental flexibility that may have accelerated the evolution of our prefrontal cortex. In essence, the volcano that nearly ended us might have catalyzed the very cognitive revolution that made us fully human. The real hope in Toba's story isn't just that we survived, but how we transformed survival into something greater. When the skies finally cleared, the scattered bands who emerged carried more than just the skills to endure. They carried the seeds of art, science, and culture. The same genetic bottleneck that nearly erased us also created a population uniquely wired for creativity and cooperation. Every cathedral, every symphony, every act of kindness across millennia traces back to those who refused to let the darkness win. Their legacy isn't written in ash, it's written in every child's laugh, every shared meal, every time humanity chooses to build rather than despair. The supervolcano tested our species, and in the crucible of that test, we didn't just persist, we became. The Toba supervolcano eruption stands as one of Earth's most defining moments, a violent intersection of geology and biology that nearly erased humanity's story before it truly began. Yet here we are, 7.8 billion strong, our very existence proof that catastrophe can be a crucible rather than an ending. The genetic bottleneck left in Toba's wake isn't just a scientific curiosity, it's a testament to the extraordinary adaptability encoded in our DNA. Those few thousand survivors passed down more than just genes, they gifted us the legacy of resilience, proving that sometimes the harshest trials forge the strongest survivors. What makes Toba's story so compelling isn't just the scale of destruction, but the ingenuity that emerged from it. When skies darkened for years, our ancestors didn't simply endure, they reinvented. They crafted finer tools to hunt smaller prey, forged alliances across tribal lines, and turned caves into canvases where art became both therapy and teaching tool. These weren't acts of desperation, but of defiance, a refusal to let the darkness extinguish creativity. The same innovative spirit that carried them through volcanic winter now drives our modern efforts to monitor supervolcanoes and develop disaster-resistant crops. History's greatest survival story continues today, not in stone tools and cave paintings, but in satellite arrays and seed vaults. As we confront modern challenges, from climate instability to the very real possibility of another supereruption, Toba's lessons take on urgent relevance. Unlike our ancestors, we possess something they could only dream of: foresight. We can track magma chambers with millimeter precision, simulate eruption scenarios with supercomputers, and store genetic diversity in Arctic vaults. But technology alone won't save us. The true lesson of Toba lies in recognizing that survival is always a collective endeavor. When catastrophe struck, it wasn't the strongest individuals who prevailed, but the most cooperative communities, those who shared knowledge, resources, and shelter. This ancient calamity holds a mirror to our modern vulnerabilities. Our globalized civilization, for all its achievements, has created fragile dependencies, just-in-time food systems, interconnected power grids, and supply chains that span continents. A Yellowstone eruption tomorrow wouldn't just test our technology, it would test our ability to come together across borders and ideologies. The hopeful truth is that we've done it before. 74,000 years ago, scattered bands of humans chose unity over isolation, and that choice echoes in every city, every hospital, every scientific collaboration today. As the ash of Toba settled, something extraordinary happened. Humanity didn't merely rebuild, it evolved. The cognitive leaps that followed, complex language, symbolic art, advanced toolmaking, suggest that adversity didn't diminish our potential but sharpened it. Today, as we peer into volcanic calderas and sequence ancient DNA, we're not just studying the past, we're continuing that legacy of transformation. Every disaster preparedness drill, every international research partnership, every community garden planted in an urban food desert is another stitch in the safety net our descendants may one day need. The supervolcano that almost ended us didn't just leave scars, it left blueprints. Blueprints for survival written in cave art and genetic code, in trade routes and innovation. Our task isn't to live in fear of the next catastrophe, but to honor those who weathered the last one by building a world resilient enough to withstand whatever comes next. After all, we are the children of survivors, and that lineage carries both a warning and a promise. The ground may shake, the skies may darken, but if history has taught us anything, it's this: humanity's story doesn't end with the eruption. It begins again. If this journey through Earth's explosive past has sparked your curiosity, consider this your invitation to keep exploring. What other forgotten catastrophes shaped human history? Could ancient plagues hold clues to modern pandemics? The conversation continues in the comments. Share your thoughts, questions, or suggestions for our next deep dive into history's greatest mysteries. And if you want to join this community of curiosity, don't forget to subscribe. After all, the next chapter of discovery is always just one click